All right, logarithms. So why are we looking at logarithms in our exponential functions chapter? Because logarithms are exponential functions. They're inverse exponential functions. So logarithm of log b to the x, okay, can be rearranged as an exponential function. And I don't like to use the bxy. I'm going to use ba and e, or log bay. Okay, so I know that a little while ago was going around as a word. I don't know if it really is anymore, but for me, it stands for base, answer, exponent. Okay, so B stands for base of an exponential function, A stands for the answer in an exponential function, and E stands for exponent. Okay, so we know where everything is. So you can rearrange something with the word log in front of it. So let's say you have a log for 16 equals 2, you can rearrange that with log bay. So this is the base, this is the answer, this is the exponent. So the base in an exponential function is 4, the answer of the exponential function is 16, and the exponent is 2. 4 squared equals 16. Okay, so it's rewritten as an exponential function. Or an exponential function can be rewritten as a logarithm. So for the first example, okay, if we look at A, B, C, and D, we're converting an exponential function to logarithmic form. So we would say log, and then the base of a logarithm, which is called a subscript, so it's just slightly lower than the actual line the log is on. Okay, that's your base of the exponential function. So log B, A is the answer. So the answer is this x here. And then after that, that's E. That's going to be the exponent of the function, 3. So we're not actually solving them yet. We're just rewriting them. Okay, for B, you have C squared is 25. So log your base, that's C. Your answer, 25. Your exponent, 2. So base, answer, exponent. Bay. So log base, 4. Answer, 81. Exponent, y. And then D, log, our base is x minus 2. Our answer is y. I'm going to put that in parentheses there. And then our exponent is 5. Okay, so you're just rearranging it to be written in the proper form. Example 2, we have logarithmic, and then we're going to write as exponential. So you have, okay, this is just on the other side. Your base is 2. Your answer is after the equal sign. Or sorry, your answer, base, answer, exponent. Your answer is x, and your exponent is 3. So base, answer, exponent. Your base in B is B. Your answer is 64. Your exponent is 3. Okay, in C, you have base, answer, exponent. So your base would be E. Your answer, 5. Your exponent, y. And then BAE for D, you have a base of x, an answer of 11, an exponent of 121. All right, now in example 3, we're going to actually evaluate these. So let's take a look here. So for A, okay, you're going to take the logarithm and you're going to convert it to exponential form. So base, answer, exponent. So we have a base of 196. We have an answer of 14. Okay, we want to know what is this exponent here. Well, how are 196 and 14 related? So when I think about that, I think, you know what? I think that the square root of 196 might be 14. So let's check that. So the square root of 196 is 14. Okay, so how do I write that as an exponent? Remember, you can write a radical as an exponent. Remember my other acronym, TIBO. The top of inside a radical, which here would be 1, okay, or sorry, the inside of the radical goes to the top of a fraction. The outside of the radical, which in this case would be to the second root, goes to the bottom. So top inside, bottom outside. So 196 to the 1/2 is the same thing as the square root of 196. And you can check that. Just do 196 to the 0.5. Okay, it's the same thing as the square root. So here, your x would be 1/2. Let's take a look at B. You have a base of 10, an answer of 100, and then an exponent of x. So 10 to what power is 100? We can go ahead, you guys can type that in the chat box. Hope we know our powers of 10 here. 10 to the second power, thank you, is 100. Okay, then for C, you have log base is 6. Your answer is 6. Your exponent is x. 6 to what power is 6? 1, good. And then here, I think that's missing an x. So the base here is 243. The answer is 1. X is our exponent. 243 to what power is 1? Or anything to what power is 1? And that's going to be 0. All right, so notice just a few things about these logarithms in example C and D. When the base and the answer are equal to each other, that's going to be 1. Okay, because the only thing that would make this base, the only exponent that would make those equal, is to the first power. Okay, when this is 1, your answer is 1, okay, that exponent is always going to be 0 because anything to the 0 power is 1. So these are just some common properties for logarithms. So, okay, if you have a 1 here in your answer spot, your answer is 0. If they're the same, it's equal to 1. Then same thing here. These are kind of properties here. If the bases are equal to each other, okay, your base and your answer, and there's an exponent here, they cancel each other out. So you just get x equals x. And then same thing here. If you have a number and then it's raised to a logarithm and that base is equal to the base of your exponent, those also cancel each other out. Okay, and then common logarithm. A common logarithm is a logarithm with a base 10. Okay, the logarithm button in your calculator, well, on the TI-83, if you hit log, that's a log with a base 10. Okay, so that is your common logarithm. Now, if you have the 84 or above, the more advanced calculators, it will put the subscript in there. So if there is nothing on the paper, like for example here, log 1 is 0, you would have to type in a base of 10 on your calculator in order to get that. Okay, and then also you have a natural logarithm. So a natural logarithm is actually a log with a base e. Okay, so a log with a base e is the same thing as your natural logarithm. So if you look at your calculator, the button for the inverse of e is ln. So you have e and ln are inversely related to each other. They will follow the same rules as logarithms, okay, whereas your 1 for your answer, you have an exponent of 0. Okay, ln and e next to each other end up canceling each other out. So you just get a 1 here. Okay, same thing here. Whatever's left here is your answer. And then e raised to the ln, again, cancels each other out. And we'll do some problems with that. Once you do a couple more problems, help you understand a little more. The graph of a logarithm, they're going to look like this. Okay, this is our graph of an exponential function. Okay, so this is your exponential. Remember, a logarithm is inverse exponential problem. So the inverse graph of an exponential function is your logarithmic graph. Okay, so it's going to have opposite values. So its domain here is going to be positive values. The range now is going to be negative infinity to infinity, whereas here, the domain and range were opposite. Okay, the domain here is all real numbers. The range is positive real numbers. We're passing through the point 1, 0 here, and then we're going to have a vertical asymptote. It's kind of over here if x equals 0. Finding the domain of a logarithmic function is really easy. Okay, all you have to do to find the domain and the asymptote of a logarithmic function is you're just going to take whatever's in the parentheses in your answers part, and you are going to set it greater than or equal to 0. Or sorry, just greater than 0, not or equal. And then you have x is greater than 5, because you would add the 5 over here. Okay, so your domain here would be 5 to infinity. So you do need to put that in interval notation. And then it will have a vertical asymptote right here of x equals 5. So let me show you how to put this in the TI-83. The 84, you should just be able to put it in like that. So if you go to y equals, here's how you're going to need to put this in if you have the 83. So log, and then you will do x minus 5, then parentheses, then you need to put your base in, so you'll do divided by log 4 for your base. Okay, and what that is the change of base formula, which has basically been eliminated with the newer model calculators, but with the older models, this is how you would put this in. And there's your graph. So if I zoom out a little bit, it's going to look more like the one on my notebook here. Or if I look at graphing technology, let's see what we've got here. So we've got log functions. Log. Nope. I want log with a base. Here we go. So log base 4, and then x is 5. And then there's my graph. All right. So that is 4.2. What do we got here? It's 11:20. So I'll give you guys about 10 minutes, work on these practice problems, and then we will come back and go over them. So in the first problem, we have $12,000 to invest, which would yield a greater amount, 6% compounded monthly, or 5.74 compounded continuously. So let's start with the monthly. Now, what I have not given you in this problem is a time period. So this one, it might depend on the amount of time. So I'm just going to use 10 years, and we're going to use that as our time period here to answer the question. It might be different with 5 years and 15 years, and we can look at that and see how close these are. Okay, so let's start with the compounding monthly. So we'll have a principal of 12,000. And let's see, 6%, 0.06. Monthly is 12 times a year. And then here I'm going to make this 12 times 10. All right, so if I'm going to go through and work this, I'm just going to go through my calculator. I'm going to do 0.06 divided by 12. Then I'm going to take that amount and add it to 1. Then I'm going to raise that to the 12 times 10, so that's 120. And then finally, the last part is I times it by 12,000. All right, so there I'm going to have $21,832.76. All right, now I'm going to look at this with the same amount of time frame, so 10 years, but with 5.74% compounded continuously. So that's going to be the PERT formula, PERT. So I have 12,000, and then my E. My rate, 5.74 as a decimal, is going to be 0.0574, and then we're going to times that by 10. All right, so let's take a look here. 12,000, second E, and that's going to be 0.0574 times 10. So $21,304.25. So at this point, the 6% compounding monthly is going to yield more. Okay, because it's a higher interest rate. So what you want to do is you want to check that this does not go higher than this at a certain point. So here, what I want to do is I'm going to check the time period here. I'm going to change this to 30 years because typically 30 years is a very long investment. So we don't usually hold stuff for longer than that. So let's try with 30 years on both of these. And just to make sure that this does not surpass this at some point because of the continuous interest. So I'm going to do the E one first. So 12,000 second E to the 0.0574 times 30. That's going to give me $67,148.50. Okay, then I'm going to look at my monthly, okay, with 30 as my time. So I'm going to do 0.06 divided by 12 plus 1. And I'm going to raise that to the 12 times 30, which should be 360. And then I'm going to multiply that by 12,000. That's still much more than this. Okay, so the higher interest rate is still going to play out. So you just want to run it through 2 scenarios of time to make sure that one of them doesn't surpass the other. So the interest rate, change in interest rate is enough of a difference where the monthly compounding is going to be higher. Let's take a look at number 2. So you have a formula. So this is just an exponential formula asking you to plug these in. Very similar to the compounding interest formula, except it does not have an n, and that just means because it compounds once a year. So the n is going to be 1 there. So this models inflation, where C is the value today, R is the annual inflation rate as a decimal, S is the inflated value T years from now. So the inflation rate in the housing market is 5.5%. How much will a $250,000 house be worth in 9 years? Okay, so very relevant question. Housing market's really booming right now. So let's say, okay, $250,000, that's going to be your C, your value today. One more zero there, okay. 1 plus our rate is 5.5%, so that's our average inflation rate. Oh, sorry, there's no n, so we don't need to put that as a fraction. So 0.055, and then in 9 years. So we would run this through as 1 plus 0.055, and we're going to raise that to the 9th power, and we're going to multiply that by 250,000. So 404,000, we're rounding to near seller 774. So 404,774. Judging by what I've seen on the housing market lately, that seems about right. Especially if you bought a house 9 years ago and then looked at today's value. I'm not quite sure it's still going to rise at that high of a rate, but stranger things have happened, so you never know. All right, number 3. So these ones, we are just evaluating our logarithm here. If there is no equals exponent after here, go ahead and add it in so that you can find that missing value. So here you have log bay. So your base is 3, your answer is 1/9, your exponent is x. So 3 to what power gives you 1/9? Well, I know that 3 squared is 9, but how did it go under the fraction? Anybody want to tell me how it got down there like that? Yeah, if I gave it a negative value, okay, then it goes down because 3 to the negative 2 is going to become 1/3 squared, which would be 1/9. So here x is going to be -2. Here, we don't really need to add an x in. Remember your rule here, anything with a 1 there is going to be 0. Okay, or if you wanted to add it in, 5 to what power is 1, that would be 0. Okay, here's your logarithm. When your base and your answer are equal to each other, they cancel out. So this log 4 and this 4 cancel. So there your answer is just what's left here, which is 8. And then let's see what we've got here. So for number 6, you have a base of 4, an answer of x minus 5, an exponent of 2. So 4, your answer is x minus 5, exponent is 2. So 4 squared equals x minus 5. So then you just work through that. So 4 squared is 16 equals x minus 5. I'm going to add a 5 to both sides. 21 is my x power. All right, so let's take a look at number 7. That's going to be a little bit different here for you. I'm going to add in my equals x. All right, so my base is 4. My answer is log 381. My exponent is x. So here I have base of 4, exponent of x, answer of log 381. Then what I want to do is I want to take this log 381 because then this can have something inside of itself. Okay, so this I'm going to move it over here. I'm going to say, well, what is log 381? Well, if 3 is my base and 81 is my answer, 3 to what power is 81? So let's take a look at that. 3 cubed is 27. 3 to the 4th is 81. So log 381 is 4. Okay, so log 381 is 4, 3 to the 4th is 81. So if log 381 is 4, then this becomes 4. So I have 4 to the x equals 4. So 4 to what power is 4? 4 to the first power is 4. So the answer there is x equals 1. All right, and that's everything for 4.2.